Okay. Three. We want three. Yes, sir. It's three. iPhone 2, iPhone 1. Okay, now save. It's no category is education. Category is education. Category is education. Category is education. Oh no. Okay, all right. Yes. Okay. 1 hour 20, right? It's gonna be 21 and 12. Okay. So good evening. This is the first compensation for the mixing lecture of SCI33206, which is physics number 5, right? For the HK school, right? Okay. I hope the sound is fine. Okay. We are live at the atomic models. We have discussed the Rutherford model, and there was a defect. Okay, there was an issue that the Rutherford model cannot well predict the behavior of light emission in terms of wavelength or spectrum
or frequency, right? Okay, an electron should spiral toward the nucleus, okay, according to the idea proposed by Rutherford. And it should also emit a continuous spectrum, okay, because with this continuous movement, okay, going into the nucleus, okay, going into the nucleus in continuous spectrum would take place for the EM radiation, and gradually lost its energy, okay, when it reaches when the electron reaches the nucleus, okay. That's the Planetary Rutherford's model, okay. According to a classical electrodynamic theory, okay, it's something about charge and movement of electric charge. The frequency of the emitted electromagnetic waves should equal the frequency of revolution of the electrons in their orbits. Okay, as the electrons radiated energy, their angular velocities would change continuously, and they would emit a continuous spectrum, right? Yeah, that's the defect by the Rutherford's model, and some further developments to atomic models will be explored later, okay. And what does the continuous spectrum mean? It means a mixture of all frequencies, okay, not the light spectrum as actually observed, okay. However, the Rutherford's model of the atom give us way to that of Niels Bohr, okay. Actually, there should be H. Oh, this is gave, okay, it's fine. Which explained the characteristic radiation emitted from the atom, okay, the Niels Bohr atoms. Okay, anyway, that's the first former generations of the atomic model, right? Yeah, as you can see, the defects in the Rutherford model, many people, okay, when you work as a physicist, you would be able to remember basic theory in physics, right? And yeah, various phenomena, including the electromagnetic radiation emitted by a heated object, which is known as black body radiation. This is gonna be discussed later. The emission of electrons by illuminated metals, known as the photoelectric effect, and the emission of sharp spectral lights by gas atoms in an electric discharge tube. This is also a photoelectric experiments. Okay, you will see it later, and could not be understood under the classical physics. Okay, the people who works in physics, which are called physicists. Okay, they can remember the classical physics, but they could not use the theory of classical physics to explain all of these. Okay, and yeah, black body. Okay, let's start with the first phenomenon which could not be well explained by the classical physics. Okay, black body is an ideal system that absorbs all radiation incident on it. Okay, yeah. As the light enters the cavity through a small opening hole, part of the light is reflected and part of the light is absorbed on each reflection from the interior walls. After many reflections, essentially all the incident ray is absorbed, okay, after several times of reflection. Well, you can take a look at this, okay, at this figure. Here is the it's like a sphere, okay, but it's a hollow sphere, okay. Actually it can have any kind of geometric shape, okay, not only sphere, but for simplicity, okay, they just draw it like a sphere. A good approximation of the black body is a small hole, okay, small hole here leading to the inside of a hollow object, okay. And you can see the blue line here, which blue straight line, which represents the ray of the light. Again, when the light hits the internal part of the thing, like 3000 Kelvin, okay, and the area under the blue curve will be less than the area under the curve by this one, okay. And the green one, which uses only 2000 Kelvin, you can see here that the area under the green curve is smaller than, much smaller than the 3000 Kelvin curve and the 4000 Kelvin curve, okay. This is from experimental data of a black body radiation with respect to the classical theory, okay. Here is the wavelength that human eyes can see, right? The relationship between the wavelength at which the curve is maximum is called lambda max, okay. Is denoted by the Greek alphabet lambda with the subscript max, okay. Max stands for the maximum wavelength, okay. When the curve is has the greatest amount of area, okay, you get the greatest area, you have lambda max, and the absolute temperature of the object emitting the radiation too, right? It depends on two factors, okay, lambda max and absolute temperature, okay. It doesn't depend on the shape, the geometric shape of the object at all, okay. It is known as Wien's displacement law, okay. This displacement law states that the product between the maximum wavelength, okay, the maximum wavelength, okay, the maximum value of the wavelength where the curve is maximal, just multiply it by t, you will get this constant, okay. And I would not give you a proof, okay. You can go to any other books to get into the detail of this expression. Anyway, let's talk about the first problem, okay. From a star observation, if the wavelength are corresponding to the maximum in the intensity versus wavelength curve is 2.3 10 raised to negative 7 meter, okay. What should its temperature be, okay? This is the maximum, okay, in intensity with respect to the wavelength curve, okay. So what we could do is that we should get back to this figure and this figure too, right? Yep. The maximum in the intensity versus wavelength curve is this value. So the peak, okay, the peak of the curve at this situation is very, very tiny. Yeah, if the wavelength corresponding to the maximum in the intensity versus wavelength curve is 2.3 Taylor's to negative 7 meter. What should its temperature be? So we need to use this expression, okay, which is the Wien's displacement law. Okay, if you want to find T, you just move lambda max to the right hand side where you get 0.289 times 10 to the negative 2 and divided by lambda max, right? And lambda max is this value, okay, 2.3 times 10 to negative 7. And yeah, if you convert it directly, you would get somehow like 100,000, okay. In yeah, let's make the division of this one. You would get 0. Blah blah blah, okay, which is 0.1257, but nowadays he is 1.257 times 10 to 4, okay, Kelvin, which is a very high temperature, okay, high value of temperature. Okay, let's go further. If you have any questions, just let me know. As usual, in 1900, okay, Max Planck developed a formula for black body radiation that completely agrees with experiments at our wavelength. Okay, if you work in electrical engineering, you have to know this one too, right? He assumed that the walls of a growing cavity were composed of billions of resonator. I think billion is 1,000, right? Billion, 1,000 million. And the reason are allowed to have only certain discrete energies, En, okay, and it's given by En equal to N H F, okay. Please note that H slash is gonna come later, okay. We are dealing with the 3D system, so the variable might be complicated, but it's not too difficult to understand for us, okay. Where N is a positive integer, okay, N is a positive integer and known as the quantum number. H is the Planck's constant given by him. Okay, this is the value of Planck, okay, or if you are able to remember, this one is gonna be very good. For me, I could not remember. Okay, on the right side you see the top view of the tube, and on the right side they use, okay, they use the reverse direction of the battery connection here. The plus polarity is on the right side and the plus polarity is on the left side, okay. And let's take a look at the left one, okay, which is the side view. Light causes the cathode to emit electrons, okay. Okay, you have here the a small stick is pointing this way, okay. Electron will prefer to move in the opposite way because electric, and it means you let the light get into this plate and you have this plate, right? And okay, the symbol of galvanometer there is now replaced by the ammeter, right? Circle with the capital A alphabet. And here, of course, as you know, in the topic of galvanometer, I have already told you that Now it's perfect, right? Okay, excellent. But this one, we have a problem. Oh, it dies already, and I don't want to waste our time for that. Okay. Yes. Again. What happened? Yes, this is the correct Wi-Fi. And what? Yeah, it's already so true, right? Okay. Anyway, let's connect again from the Streamlab. Okay. This one, right? Yeah. Once the electron collects the energy from the light, okay, it will escape the emitter and it will end at the collector, okay, collector's plate. And here is the kind of photoelectric experiment, okay, which lies in the same kind by Hawax and Leonard, okay, two people. And what we could observe from this experiment is that the experiments show that the light incident on certain metallic surfaces causes the emission of electrons from the surfaces. Okay, in that plate, this anode and cathode plate should be made of a kind of metal, right? Electrons are emitted from the surface almost instantaneously. Okay, less than nanosecond. Okay, which is very, very short. After the surface is illuminated, even at low light intensities. Okay, the light intensity has no big effect to this photoelectric study. Okay, classical theory would predict that the photoelectrons, the electron that escape from the metal is called photoelectrons. All right, require some time to absorb the incident radiation before they acquire enough kinetic energy to escape from the metal. Okay, but it's not the case, right? It just go almost immediately, only nanosecond. Okay, the electron flow stops completely only when the reverse potential difference V is made large enough. Okay, this is the case when we leave the reverse polarity to the initial experiment. Okay, and this one should be light enough and it can stop electron or prevent electron from moving to from this side to from the cathode to the anode. Okay, you should have enough voltage or in this direction. Okay, electron flow stop completely. Okay, if we use the large value for the potential difference V, or more precisely, the corresponding potential energy EV. Okay, you know E is the elementary charge of the electron. You know, it's the charge value for the electron. Okay, and yes, V is the potential difference here at the power supply. Okay, V is there. It's greater than the maximum kinetic energy, which is given by Kmax. Okay, Kmax is the maximum kinetic energy. Okay, you just pick up the electrons that has the maximum speed, okay, and that's denoted by Vmax. Okay, Vmax is the maximum velocity of the electrons. You just pick up the electron that has the maximum speed, and we multiply it with the mass of electron, right? It's 9.110 to negative 31 or something like that. And here is the square of the velocity, okay, the maximum velocity, and all of these is divided by number 2, okay, which is given by Kmax equal 1 by 2 me v square max. Okay, the reverse potential difference required to stop the electron flow completely is called the stopping potential, okay, which is denoted by capital V. Okay, and here the mass of electron is 9.1, as I told you here, okay, times 10 to negative 31, and for the charge of the electron it's 1.602. okay, you just, for simplicity, you can use only the first few digits, okay, you may not need to use complete the long digits of electron charge or the electron mass at all, right? And Vmax is the maximum velocity of the electrons, that what we have already talked about. The stopping potential, right, Vs, could be found from the equality of EV to 1 by 2 MeV max square, okay? Just move E to the, okay, it is given by EVS, okay, EVS equal 1 by 2 mv square max, okay, and then you move E to the right hand side, okay, you're gonna get Vs, okay, the stopping potential difference like this, okay, it's 1 by 2 and E, right? E is 1.6 times 10 to negative 19 coulomb, right? And measuring the stopping potential Vs therefore gives us a direct measurement of the maximum kinetic energy, okay, because it's the same thing, okay. If you know Vs, you can also know the maximum kinetic energy, okay. You just multiply Vs, the stopping potential, by the electron charge 1.6 times 10 to negative 19, okay, you get the maximum kinetic energy immediately. So if you measure the stopping criteria, you can also infer to the maximum kinetic energy of the electrons, okay. In the electrons have once that the maximum kinetic energy that the electrons have once they leave the cathode, okay, they start to have speed, okay. With the first setup, okay, they vary the intensity of the light, okay. Of course, you use the light with this one, and if you increase the intensity of the light, what is going on, okay, and you just take the value from the ammeter, okay, the current on the y-axis, that when in the potential difference of the voltage by a voltmeter, and on the x-axis, right, and it's turned to be something like this, okay. The voltage is on the x-axis, that in the current is on the y-axis, right? In once we use the low light intensity, the light with low intensity, which is denoted by the blue curve here, okay, Okay, both situations start from the same stopping potential minus delta Vs or whatever you want to use. Okay, whatever symbol you want to use, and once you apply more volts to this one, okay, not the levers, the typical photo tube, okay, this one, okay, plus to the anode and negative to the cathode. Where is that? Okay, here. Okay, once you have you let the light with low intensity get into the phototube. When you increase the voltage, the current will not be increased anymore. Okay, it gets saturation, and but for this region, it increased a lot. Okay, the current increased a lot once we increase the applied voltage, but at a certain value of the applied voltage, we get a flat curve for the current. Okay, and once you use higher intensity of light to get into the phototube, we get the red curve here as the result from the experiment. Okay. Okay, of course, it starts from the same point of the stopping potential. Okay, it's a negative value, actually. And the high intensity will give us also higher amount of current flowing inside the phototube here. Okay, the phototube. If we use higher voltage source, okay, we just adjust the voltage here. You could get the higher amount of current. Okay, the current will flow here stronger. What else? Okay, the current increases with the intensity but reaches a saturation level for a large value of delta V. Okay, and once you increase more voltage, then you could not get more current. So it's not the same as the Ohm's law curve, right? If you increase the voltage, you could get more current, right? That's the result by Ohm's law. But it's not the case here for photo electric tube. So what we could observe from this one is the following. Let me open again the good note. We don't use the 5th chapter anymore, right? This is 308. No, we use the new version, which is 20 here. Okay, here. From this figure, you can see that the classical wave theory predicts that when we increase, okay, this is the own theory first. Okay, let's take a look at the own prediction. It's called classical wave theory. When we increase the intensity of the light, okay, striking the cathode, we increase the light, the intensity of the light striking the cathode. It means we let the light, a larger amount of light, okay, get into the cathode, the plate here. Okay, in yes, the electrons should come off with greater energy. Okay, from the classical wave theory, we should get more electron. Okay, when we have more lights incident on this plate. That's the prediction by the classical wave theory. And the stopping potential should be great. The stopping potential should be greater too, right? But it's not the case. As you look here at the result from the experiment, we could not get higher currents. Okay, the number of more electron could not take place, could not happen. Okay, it just saturated in the what is that? The stopping voltage or stopping potential is not larger too, right? You can see that whether we use low intensity of light or high intensity of light, we get the same value of stopping potential. It's not what the classical wave theory predicts. Okay, they predict that the stopping potential should be greater when we use the higher intensity. It means the red one should have the stopping potential somewhere here, but it's not the case. Okay, this is the realistic result from the experiment, so we need to believe on this. Okay, let's go to the next slide. It's something about what is that? Kmax. Kmax is the kinetic, the maximum value of the kinetic energy, right? Maximum, simply speaking, the maximum kinetic energy. And on the x-axis, it is the frequency of the light. Okay, once we let the light get into this tube, the light will hit the cathode, right? And let's take a look at the frequency of the light. Not every value of the frequency of the light we will get the electron moving out of the cathode plate. Okay, once there is no electron move out of the cathode plate, the velocity of everything is 0, so there will be no kinetic energy at all. Okay, and once the light attains a certain value, which is denoted by F with subscript C here. Okay, we will talk about that later. What does the subscript mean? Okay, once the frequency of the light is greater than this value, electron start to get out of the cathode plate and it reaches the anode and it flows in this way. Okay, and that will make the current take place in this experiment. Okay, we need to have a certain value of the frequency that the electrons start to get out of the cathode plate. Okay, and the relation between the frequency and the kinetic energy is straight, is linear. Okay, is a linear way, is in a linear way. Okay, what else? This one is called what is that? See, critical frequency, or sometimes it's called threshold frequency. Or no, not critical, it's called cut-off frequency. Okay, cut-off frequency. And then the wave theory predicts that the current should occur at any frequency, but it's not the case. Okay, we borrow the theory from the classical way, and we found that it's not valid. Okay. The classical wave theory predicts that the current should take place everywhere for the frequency, because it doesn't depend. The formula doesn't depend on the frequency, but you can see here from the realistic experiment result, it depends on the frequency, and it starts to have current movement or the kinetic energy of the electron from a certain value of the frequency, and no electrons are emitted if the incident light frequency fall below some cutoff frequency. Okay, there is no electron movement at all if your frequency is lower than this value. Okay, and denote this frequency is denoted by FC. FC is known as cutoff frequency. Okay, or sometimes it's known as threshold frequency. Okay, whatever they call, okay, in different situation they would use different words, but the meaning is the starting frequency that we could get electron moving out of the cathode plate, and when once they move they have the speed, and the maximum value of the speed is will give us the maximum kinetic energy here. All right, and let's take a look at the second aspect. You have already really or change the intensity of the light, right? It's better to get it at the middle. Okay, yes, okay, this is the stopping potential, right? It's in the reverse way because it's left in the reverse way. That's why it's get the negative value. Okay, we now change to frequency of the light. Okay, we may use the F1. Okay, let's say the light of F1 has lower frequency than the light of F2. Okay, F2 is the second frequency. Let's say the second frequency is greater than the first frequency, and yeah, you can see here that you start from lower frequency, you have greater stopping potential. Okay, and if you have a higher frequency, you have lower stopping frequency. Okay, and for whatever value of the frequency, you will get the saturation of the current here. Okay, and yeah, it's gonna remain constant. It will be flat all the time. And VAC is the voltage across the anode side and the cathode side. We say it's anode and cathode. Okay, and yeah, VAC is the potential of the anode with respect to the cathode. Okay, in this is the figure of the photoelectric current versus applied potential difference. Okay, in figure 17. Okay, that's the figure here. Where is figure? Okay, in this figure, this one, figure 17, or this one. In figure 17, when the frequency of the light is increased, okay, the stopping potential increases linearly. Okay, the stopping frequency also increases linearly, but it's in the negative side. Okay, it increases in the negative side. You can say it increased because it's if you take a look at the reverse way, like this. Okay, if you take a look at the reverse way, it means it increased. All right. What happened? Yeah. In in figure 17, this one, the frequency of the light is increased. The stopping potential increases linearly. Okay. Yeah. If you increase the frequency, you need to have more voltage in this direction. And from figure 15 to figure 17, it is important to note that the maximum kinetic energy 1/2 MeV max square, this is the maximum kinetic energy, equal EVS. Okay, doesn't depend on the intensity. Okay, if you take a look at the figure 15, the maximum kinetic energy or the stopping potential doesn't depend on the intensity of the light at all, and that's why whether you use the high intensity of light or low intensity of light, you get the same stopping potential here. And the maximum kinetic energy depends on the frequency of the wavelength. Yes, you can see here you get larger or greater value of the stopping potential once you use the higher frequency of the light. Okay, and the prediction may not be so good, right? But before that, we have the expression of the energy, right? I forget to talk about this. Okay, on page 27 in 1900, Max Planck developed a formula of the black body radiation, and that completely. Oh, I forget to talk about the Wien formula, right? Oh, I'm stupid. The Wien's formula, right? Oh my God, stupid. That's the total radiation emitted. The area under the curve, okay, increase with the increasing temperature. When you have hotter object, okay, you get more intensity of the light. Okay, well, you may notice this effect, right? If you go to the shop that they try to make some kind of knife, okay, they have to heat the knife, okay, in the red color, and yeah, you can see that if you take the energy to the metal, you get more light, okay, which is actually the more intensity. Okay, experimental data of black body radiation with respect to the classical theory, this one, right? In the relationship between the wavelength at which the curve is maximal and the absolute temperature of the object emitting the radiation, which is the variable T. The product of these two things is captured by this person, Wien, okay? And it's known as the Wien's displacement law, which is given by lambda max T times T, which is the absolute temperature. Okay, the absolute temperature means the temperature in Kelvin, right? That's what you have seen in the last semester, the previous semester. From a star observation, if the wavelength corresponding to the maximum in the intensity versus wavelength curve is 2.3 times 10 to negative 7 meter, that's the wavelength of the light, okay, from a star. Okay, this is the maximum value of the wavelength you could get from the curve of the light intensity from that star, and the peak of that curve correspond to 2.3 times 10 to negative 7 meter. What is that? It's somehow 230 nanometer. Okay, and what should its temperature be? Okay, so you just apply the Wien's formula. Because you want to know the temperature, just move the lambda max to the right hand side, you get this one. All right, you get 0.289 times 10 to negative 2, and the unit of this expression, of course, it's the unit of the wavelength is meter and the unit of the temperature is Kelvin. You get meter times Kelvin as unit in the Wien expression, right? And if you move lambda to the right hand side, you get 0.289 times 10 to negative 2 divided by lambda max, right? We have already moved lambda max to the right hand side, and lambda max is the value on the x-axis of the curve, but this curve should be observed from this star, okay, the star, whatever the star, okay, but it's far away from, extremely far away from our Earth. But the physicists observe this one, right? Observe the spectrum or the intensity of the light with respect to the wavelength, okay? And we leave the lambda max at the denominator position, okay, the lower position of this ratio, and we leave all these numbers into the calculator. We get this one, which is 1.257 10 to 4. Okay, it's 10,000. Okay. Simply speaking, we say it's 12,570 Kelvin, right? That star should have extremely high temperature. Okay, it's 12,000. All right. The water is boiled at 373 Kelvin, right? But this one is 12,570 Kelvin. Oh, it's extremely high. Okay, in 1900, Max Planck developed the formula for the black body radiation, and that completely agrees with the explained at all wavelengths in this one, right? Okay. That's the first era of the quantum physics. He assumed the walls of the growing cavity were composed of billions of resonators. Okay, he assumed that here. Okay, inside this black body, there are billions resonators. It's a kind of, okay, they didn't know that it's the behavior of electrons and so on. They say that there should be some tiny elements vibrating inside this body. Okay, and that one is called resonator. Okay, the particle that vibrates all the time inside this body is called vibrator. Resonators. And the resonator are allowed to have only certain discrete energies. You can see that physicists needs a lot of imagination. Okay, if you cannot completely explain something, you need to use your brain to create or make the imagination, okay, which may be true or may be not true in the future, okay, but the people in the future will try to verify your idea, your imagination, whether it's true or not, okay. Yeah, Planck imagined that there are billions resonators inside this black body, and each resonator or all resonators are allowed to have only certain discrete energy. Okay, they could not have continuous energy, and they say Planck proved that. But according to the high school level, we will not get into the deep detail of how Max Planck arrived at this expression. Okay, the energy at the end state in level is equal to n times h. Okay, please don't ask me right now what is this. F, okay, 3 variable n h f, okay, where the first variable n is a positive integer. It's known as quantum number, and h is the Planck's constant given by this value 6.6 blah blah blah. Okay, 10 to negative 34, and you can imagine that 10 to negative 34 is a very small very small quantity. Okay, but if you go further in this chapter, sometimes the Planck's constant is going to be represented in a proper unit, which is called electron volt. Okay, but right now we see the Planck constant in the SI scale, okay, Joule and second, but it appears in a very, very tiny order, -34, okay, of the 10. Okay, F is the frequency of the subatomic vibration of the chain of the charges, okay. He assumed that there would be resonator, and that resonator should be charges, right? Should be whether it's positive charge or negative charge. He didn't know at that time, but the vibration of that charge, okay, will follow this frequency, okay. Those subatomic, microscopic elements should have the vibration with this frequency, okay, F. And yes, based on this, okay, Albert Einstein, okay, Albert Einstein is a well-known physicist, right? 5 years later, Einstein took the formula by Max Planck. Okay, he just tried to explain what's going on inside the photo tube or photoelectric study here. Okay, Einstein used the Planck's formula, okay, and create a theory to explain what happens in the photoelectric effect. Albert Einstein proposed the existence of discrete energy packets during the transmission of light. Okay, of course, we know from the last semester that light is the kind of electromagnetic wave, right? But no, it's not the case. Albert Einstein wants to explain what's going on here, right? And he proposed, or he suggests that no, the light is composed of a small unit of energy, actually, and that small unit of energy is called photon. Okay, you know photo, right? Photo is an image or something else, right? A photon is like a particle, but it's energy particle. Okay, small, very, very extremely small energy particle. And Albert Einstein extend the Planck's concept of quantization to electromagnetic waves. Now, electromagnetic waves is not wave anymore. Okay, it's a kind of particle. Okay, small particle or tiny particle. And a photon, which is known as light quantum, or also known as a tiny energy packet. The photon is emitted due to the jump from a quantized oscillator, okay, inside this vibration, right? Electron, oh no, the photon exists, okay, or gets out of this internal of the black body. It means that it's jump from the quantized oscillator from energy state En, which is equal to NHF, right, from the Planck formula, this one, Planck formula, to the next lower state, which is En minus 1, N minus 1 times H and F, right? And the photon energy could be found from the energy conservation, which is the negative value of this difference, right? And if you go further in bachelor degree, they use the gamma, a kind of gamma, to represent the photon, okay, in standard elementary table. And photon energy could be found from this expression, the negative difference of the energy, okay, and energy in physics, right, the delta of any situation Start is the difference between the final state and the initial state, right? The final state stay first and the initial state stay later, right? And once you distribute the negative, it means the initial stay first and the final stay at the end, right? And yes, the final state is this one, right? The next lower state, and the initial state is en. Okay, you make the subtraction of these two terms, you get hf. Okay, and that's the simple formula, and it is known as Planck-Einstein relation. Okay, this one E equal hf. Okay, which is a very well known formula. And photon can give all its energy hf to a single electron in the metal, and here is the point where Albert Einstein tried to explain what's going on in this experiment, the experiment by Howard and Leonard. Okay, because at that time it was really popular. Okay, many people, many physicists pay attention to this study. Okay, now but the time is over. We will continue our lecture next time. Okay, about the work function, which is the result from the photo electric effect. โอเควันนี้ก็เลคเชอร์ที่ชดเชยนะครับก็คงต้องจบไว้ก่อนเพียงเท่านี้นะครับอาจจะมีขัดข้องบ้างนะครับจากการที่อัดไว้นะครับก็หนึ่งก็คือมือถือมันเก่านะครับ iPhone 5 แล้วก็ของ iPhone 13 นี่ใช้ได้อยู่ iPad ใช้ได้อยู่นะครับจะมีปัญหาเรื่องอินเทอร์เน็ตค้างบ้างระหว่างทางนะครับแต่ตอนนี้ก็สมูทแล้วนะครับโอเคเดี๋ยวอัดคลิปให้อีกครั้งหนึ่งนะครับสำหรับการชดเชยนะครับตามที่คุณเรียกร้องครับวันนี้ก็จบไปก่อนนะครับสวัสดีครับบ๊ายบายครับ